Mutable references have one big restriction. You can only have one mutable reference to a particular piece of data in a particular scope. This code will fail. Let mut s equal string from hello. Let r1 equal reference to mut s. Let r2 equal reference to mut s. And then print them both. So here we are. Borrow fail. Cannot borrow s as mutable more than once at a time. Let's watch it fail. Yeah. So we have first mutable borrow occurs here for R1. Second mutable borrow occurs here for R2. This restriction allows for mutation, but in a very controlled fashion. It's something that new Rustaceans struggle with because most languages let you mutate whenever you'd like. The benefit of having this restriction is that Rust can prevent data races at compile time. A data race is similar to a race condition and happens when these three behaviors occur. Two or more pointers access the same data at the same time. At least one of the pointers is being used to write to the data. There's no mechanism being used to synchronize access to the data. Data races cause undefined behavior and can be difficult to diagnose and fix when you're trying to track them down at runtime. Rust prevents this problem from happening because it won't even compile code with data races. As always, we can just use curly brackets to create a new scope, allowing for multiple mutable references, just not simultaneous ones. So here they just put let r equal mutable reference to s in braces. And it says r goes out of scope here. R1 goes out of scope at the close brace. So we can make a new reference with no problem. Below we have let r2 equal and mut s. It's true. So oof. I'm gonna switch my function from borrow fail to scope fail. So comment borrow fail and uncomment. What? II is not the same as DD. There we are. Uncomment scope fail. I should do it. So now what we're looking at is scope fail. Excuse me. So we have let mut s equal string from hello. And we create a new scope with some braces, and in that scope we let r1 equal a reference to mut s. And we end that scope. And then back in the main scope, I guess, or the, function scope, let r2 equal and mut s. So no problems there. It does have a problem if you then try to use both of them in a little println or something, because this is R1 is no longer in scope after this brace, close brace. And down here we have help. A local variable with a similar name exists, R2. Yeah, but it cannot find value R1 in this scope. So let's see what we say here. So we can use curly brackets to create a new scope, allowing for multiple mutable references, just not simultaneous ones. Right. A similar rule exists for combining mutable and immutable references. This code results in an error. Let mut s equal string from hello. Let R1 equal reference to s. No problem. Let R2 equal reference to s. No problem. Let R3 equal mutable reference to s. Big problem. Then they bring the println back. Println R1, R2, R3. Excuse me. So let's go ahead and bring mute fail into it. Let's uncomment mute fail. So now, yeah, take this and put it here. Blam, mute fail, and then in the function, in the main function. Wait, that's not what I want to do. Mute fail, that's the one. Come back. So mute fail. I wonder if I can, oops. That's not what I was really trying to do. Who cares? I do. I care a little bit. What about this? What if I say, so visual, bump it over one, replace with blam. Oh well. Alright, so now we're looking at mute fail. We've got let mut s equal string from hello. And then let R1, oh, it's a reference. That's why they're calling it R1. Nice. Let R1 equal reference to S. Let R2 equal reference to S. Let R3 equal mutable reference to S. Cannot borrow S as mutable, because it's also borrowed as immutable. Well, sometimes it's fun to cargo run. Here we go. Yep, mutable borrow occurs here. Here's the error. Immutable borrow, later used here. Mutable borrow occurs here. Woo! Woo! We also cannot have a mutable reference while we have an immutable one. Users of an immutable reference don't expect the values to suddenly change out from under them. However, multiple immutable references are okay because no one who is just reading the data has the ability to affect anyone else's reading of the data. We have personified functions. I like it. Note that a reference's scope starts from where it is introduced and continues through the last time that reference is used. For instance, this code will compile because the last usage of the immutable references occurs before the mutable reference is introduced. So we got the no problem, no problem. Oh, and then we say println. We use them. Yeah. So are they dropped out of scope? I guess we're not talking about, no, not dropped. Dropped is a thing that happens to data in the heap. But these are on the stack, so I guess we can't say that they're dropped, but they do leave scope, I guess. Well, excuse me. So what it's saying is if we take this and put it there, and then, oops, oof, oh right, okay, so delete to that, escape. You saw me escape. Well, if you were looking, I guess you saw me escape and hit A at the same time with my big sloppy hands. So now we will delete till the close paren escape. Good clean escape. Alright. So then I'm gonna put a little space there. Give us a little visual separation. And now we want just this one. Let's go this way with it. Delete till that. Oh. Right. Vim can't read my mind. I have to tell it with a different keystroke which way to go. Well, we'll say delete till. That's not going to work. Delete till the second. Oh. Okay, fine. Wah, 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 wah. So now we want to just get rid of everything but R3. Let's do this. We'll make this be R3. Blam. Oh yeah. So DVP. Programmer's Dvorak. I actually have to hit Shift if I want numbers. They're in the Shift layer. So let's do it again. Alright, and now we will delete till the close paren. Okay. Looks good. Give it a run. Put that in the middle of the screen. I would like for it to go up further. Can I just keep scrolling? Yeah. Cargo run. Hello, hello, hello. Hello. Hello there. The scopes of the immutable references R1 and R2 end after the print line, where they are last used, which is before the mutable reference R3 is created. These scopes don't overlap, so this code is allowed. Even though borrowing errors may be frustrating at times, remember that it's the Rust compiler pointing out a potential bug early at compile time rather than at runtime, and showing you exactly where the problem is. Then you don't have to track down why your data isn't what you thought it was. I really think that, okay, so I'm learning to program, right? And I think the Rust language is good for it. Even though it's so picky, I think it's really helpful for learning. Dangling references. In languages with pointers, it's easy to erroneously create a dangling pointer, a pointer that references a location in memory that may have been given to someone else by freeing some memory while preserving a pointer to that memory. In Rust, by contrast, the compiler guarantees that references will never be dangling references. If you have a reference to some data, the compiler will ensure that the data will not go out of scope before the reference to the data does. let's try to create a dangling reference, which Rust will prevent with a compile time error. We got our function main, let reference to nothing equal dangle, equal the dangle. So we're bringing into scope a variable called reference to nothing. And on the right side of that statement is the function dangle. Okay, so here's the function dangle. Fandangle outputs a reference to a string. And then in the function body we have let s equal string from hello. Okay. So it creates a string. And then lonely at the bottom here is a reference to the string. Okay, well, I didn't understand that immediately, so let's go ahead and that's not it. And yeah. Cargo. Run. Yes, it do. Okay. Here's the error. Missing lifetime specifier. Fandangle outputs a reference to string, but here it says it expected a lifetime parameter. Help! This function's return type contains a borrowed value, but there is no value for it to be borrowed from. Help! Consider giving it a static lifetime. This error message refers to a feature we haven't covered yet, lifetimes. We'll discuss lifetimes in detail in Chapter 10, but if you disregard the parts about lifetimes, the message does contain the key to why this code is a problem. This function's return type contains a borrowed value, but there is no value for it to be borrowed from. Let's take a closer look at exactly what's happening at each stage of our dangle code. So, function dangle. Dangle returns a reference to a string. Okay. And then s is a new string. And then we return a reference to the string s, but then a closing brace. Here, s goes out of scope and is dropped. Its memory goes away. Danger. Because s is created inside dangle. When the code of dangle is finished, s will be deallocated. But we tried to return a reference to it. That means this reference would be pointing to an invalid string. That's no good. Rust won't let us do this. The solution here is to return the string directly. Function noDangle results in a string. Let s equal string from hello, and then I guess this is the, because there's no semicolon and it's the last thing all by itself, so this is the result s. This works without any problems. Ownership is moved out and nothing is deallocated. Alright. Function noDangle, and then we have blap, and then we have boom. Right, so now, oops, come back. Reference to oof. That was a change inner word. What I wanted was change word. Reference to everything equals equals, let's call it dongle. That's fun. Good times. Hey, look at that. Lovely. Ah! Click. Yay! I did it. Didn't do anything with it, but there it goes. The rules of references. Let's recap what we've discussed about references. At any given time, you can have either one, you have to choose. You can't have both. At any given time, you can have either one mutable reference or all the immutable references you want. Because you can either have a bunch of functions who know about, oh gosh, you can, okay, so there's a string and it's like a buried treasure, and references are treasure maps. So you can hand out all the treasure maps you want, as long as you hand it out to people who aren't gonna take a treasure or add to the treasure or anything. Or see, because they need to see the treasure. They're gonna like what do you call it? What do you do when you got a house? You're like, you're gonna sell it, or you're gonna buy a house, and you got a guy who comes in, inspector. That's not what I was looking for. So you've got a bunch of functions can have treasure maps, as long as none of those functions are going to change the treasure, because then the next one will come back in, will follow the treasure map, and get in there and look at it and be like, whoa, somebody changed the function. I mean, somebody changed the treasure. Wow, the string. And then you can't have, well, you can do that. You can have all the treasure maps you want, as long as nobody can get in there and mess. Or a closely guarded secret passed down from scope to scope. One map. And you can go change the treasure. References must always be valid. That does not quite ring a bell. Valid reference. References must be valid. Does that mean they must be in scope? Ooh. That's, I mean, I guess I could search for valid on this page. I'll try it. Oh, come on. Yeah, there we go. Valid reference. The scope in which the variable s is valid is the same as any function parameter scope. Here we have which is the scope for which that reference is valid. Okay, so valid is just another word for in scope. Oopsie. Next up, slices.